طيب, Bismillah ar-Rahman ar-Rahim. So last time we stopped here. So we talked about the UTP or unshielded twisted pair cable. We talked about the insulation parts. We had two layers of insulation. One to insulate the energy inside the each wire separately, okay. And there is one that's used in the case of shielded twisted pair or STP. It's coming. We will touch a little bit on this again, which is used to as an insulation layer for interference from outside on the wires. And we said that for the case of twisted pair, this layer is probably not needed because it increases the cost without adding any gain. So for coaxial, the same exact concepts. So we have, in that case, we have one thick copper wire, and we have what we call the plastic insulation as well for, again, focusing the energy inside. And then we have the braided copper shielding. The braided copper shielding is for protecting from outside. One thing to pay attention to here is that this thick wire itself, it can carry wider bandwidth compared to the thin wires used in the case of twisted pair. If we compare this wire with one single wire from the twisted pair cable. However, the twisted pair, as we said, because we have 8 wires, so each one of them can be used to carry part of the signal. You will learn this in details in Network 2 next semester probably. Some of you will take Network 2. So in that case, the twisted pair in general can carry wider bandwidths if we consider all the 8 wires together. And as a result, it also can carry higher bit rate compared to coaxial. Okay, even though the one important advantage for coaxial in that case is that since it's a thick wire, it can carry the analog signal for a longer distance. So probably the coaxial length limit can reach up to maybe 500 meters. Whereas for the case of unshielded twisted pair and twisted pair, it's typically around 100 meters only. Okay, so that's one advantage for the case of coaxial over the twisted pair. In the past, we used to, before the days of hubs and switches, we used to create the shared medium topology using these connectors. As I explained to you before, coaxial was actually more commonly used, more than unshielded twisted pair, for the shared medium axis topology. And what happens is that we have nodes like this with wires, and then we have some of these connectors are used as T connectors here. Okay, and then so you have these connectors, like you have T connector, and then you have a coaxial wire like this. So this actually explains the physical and logical topology. So the physical topology in that case is the same like the analog to the logical topology, because there's no hub or switch. Okay. T connector, it's like T connector is like this. Yeah, so you have one hole here, and you have 2 holes here to connect. So in the last node there is like a termination connector that gets. So this termination connector, the signal goes through this termination connector and reflects back, so that it stays in the medium. So this is in the very early days. We are not using this anymore. Of course, hubs are becoming very cheap. In fact, nowadays it's almost get it for like 1 real. So we're not using this because, well, you can feel that connecting all these connectors here and there is kind of, it's hard. Whereas connecting all these cables into one hub, it's very easy. So this is the use of these connectors. That's why here we have multiple types of connectors. Some of these are T connectors, some of these are termination connectors, some of these are connect only one machine, and so on. And then we have the outer jacket, which, as we said before, this is only for packaging, to package everything together. This is the shielded twisted pair. The main difference here is that each pair will have one insulation in addition to the braided insulation, and that's why it's higher cost. And in terms of protecting from interference, the gain here is really minimal compared to the cost. Remember that these wires tend to span for long distance, so if you have long distance of this plastic insulation, that increases the cost significantly. And that's why we normally use unshielded twisted pair instead, which is efficient from the cost and interference perspective. Fiber optics is much more complicated because fiber optics is, as you can imagine, is made of glass, right? So for glass, as we can imagine, glass can be broken easily. So that's why we need some kind of special handlings. So we have the core, and the core is like a small glass strip, which again is covered by the cladding, and again the cladding is used to focus, in that case, the light beam. So it focuses the light beam inside the core. So if you were to have this is for example the core, okay. So the cladding itself adds on top of it like some layer, okay, so that if the light gets all the way up here, it reflects the light back. So it goes here and it reflects back. So the light beam keeps inside the core because if you don't have this cladding, what happens is that the light, some of it may actually deflect outside. So you lose a part of the energy. So the cladding helps this beam to stay inside the core. Okay, so this way it can go a longer distance without losing much energy. So and again the buffer is used to protect the light energy from outside interference. Here there is another layer of strengthening material, and the reason for this is that we have a glass, so the strengthening material tries to keep the core glass without sharp bends. So if you try to bend it, it will bend a little bit, but it will bend smoothly so that the core does not have sharp bends. So this material helps the glass from being broken easily. So this way the core will be a little bit tolerable to bending, but not very sharp bending. And that's why the fiber optics, usually they require some special skills. We cannot just you cannot, anyone who is trained, it would not be wise for him or her to deal with fiber optics, because you can easily try to bend it sharply, and this causes the core inside to break, and you don't know. So this way you try to connect it, you're not getting any communication, you don't know what's going on. So it needs some careful handling. It needs somebody who's trained to deal with it, so you know that what is the extent of the bending that's barely enough to just keep it or to avoid breaking the core inside. And that limits the use of fiber optics as well in some environments that requires some maneuvering in terms of how you connect the cable. For example, if you want to have the wire going from one rod to another, then you have to take it all the way and then bend it and then take it all the way again in order to cover multiple rows. And fiber optics is not the way to do that. So fiber optics will be good if you have like a straightforward connection to some extent. But if you have environment that restricts you to have sharp bends, then it's better in that case to use UTP. But UTP, of course, has much less bandwidth compared to fiber optics. Has huge amount of bandwidth. I once read an article that the theoretical bandwidth of a fiber optic can reach up to I think 6 terabits per second, something like that, which is enough to carry probably the traffic from a continent, a whole continent, or like many countries together. This is the theoretical bandwidth. Again, in terms of practical bandwidth on the fiber optics, you don't have devices that can use light continuously for a very long distance, because you have to connect routers at some point, and routers, we don't have optical routers, yes. At least until today. So routers at the end of the day have to be wired or wireless or something like that. So which means that you have to convert, you are restricted at some point to convert the light beam into electrical beam. Once you have this conversion, you lost the benefit of fiber optics. So that's why fiber optics are used for submarine cables a lot. So submarine cables that connects a country with the internet, for example, under ocean or under the sea. So you have multiple of these fiber optic wires under the ocean to aggregate all the traffic from multiple countries or from a single country to the outside world, to the internet. So the typical or the maximum bandwidth that you can get from the fiber optics is not more than, I think it's now around 1.5 terabits per second for one single fiber optics. But the theoretical bandwidth is not achievable given all the devices that we have nowadays. Okay, so it has very large and wide bandwidth, and it's much more expensive, of course, compared to UTP. So nowadays in Qatar we are blessed to have fiber to home. So this theoretically means that you can have a huge amount of traffic on this fiber coming out from your home. So that gives you the ability to expand, all types of services in your home without having to have fundamental changes to the network. So that's why we have nowadays we have Mosaic and we have all these services, and everything is carried over the fiber optics. So the limitation becomes at Ooredoo's side. So Ooredoo wants to give you this small pipe, so they will restrict the traffic from their side. But in terms of medium, the medium can carry whatever traffic you want. So the limitation here comes from Ooredoo. So Ooredoo can give you a plan of, they can easily give you a plan now of 10 megabits per second or something. But the limitation becomes on their network, if their network really can carry this amount of traffic from multiple users. Okay, so there are two types of fiber optic, and that depends on two things: on the core glass and on the device that you use to generate the light beam. On two things, not on one. So for example, you have the single mode and you have the multi-mode. For a single mode, what happens is that you need a very, very sensitive light beam generator, which generates the light in a specific narrow beam, okay, so that the light can go in a straight line along the core without having to do these reflections inside. Okay, so that requires, of course, very, very sensitive light generators.
Laser in this case?
Laser in that case, pretty much, yes. So the core itself, in terms of glass, is very thin. I think it's 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 the small core. It's 8 to 10 microns. This is extremely thin. Okay, and you can imagine that with this thin radius, it can be broken very easily. So you need really special strengthening material to keep it, from being broken. The laser generator in that case generates the light beam, and it goes into a straight line inside the core. And because you don't have any energy dissipation or any reflections inside the core, the energy is focused in a straight line. So that helps the light beam to travel for a longer distance. Okay, so so that's why the distance in terms of, for the case of the single mode, can get up to 100 kilometers. So so someone might ask, 100 kilometers is usually not enough to go under the sea or under the so that's why you need some stations, some intermediary stations under the sea to take the light beam and then strengthen it or regenerate it in such a way that allows it to go into another 100 kilometer or something like this. So 100 kilometer is not does not necessarily mean that this is the limit in terms of the distance that you can go, but you can connect some intermediary stations to increase that. Similar to what we do for the case of UTP. So UTP has the limit of 100 meters, but if you connect a hub or a switch after 100 meters, then you can go for another 100 meters. Okay, so here is, for this case, it's 100 kilometers. So it's 1,000 times. For the case of multimode, of course, because of the reflections inside, of course, the core glass has a thicker radius or a larger radius. In that case, it's about maybe 5 times the radius. And because of the light source can be a small LED or any non-sensitive device that can generate light using multiple wavelengths, and in that case the different wavelengths will go into multiple paths inside the core, and they can reflect. Of course, the cladding will help it to reflect inside, but the fact that it creates multiple wavelengths like this restricts the distance, the maximum distance that it travels. So in that case, instead of 100 kilometers, it gets down to probably around 2 kilometers or less. Well, it depends. This is good for connecting in data centers, for example. And if you have seen like some data centers, they receive from multiple networks, like here in the university, for example, from multiple switches and things like that. They receive aggregated traffic, and then you need just a small fiber optic that connects you to the optical switch, which can then connect you to Ooredoo. So this is probably more fit to aggregate the traffic from multiple networks. But here, it's probably capable of loading maybe or carrying the traffic from a whole country. But the different types, they have different usages. Okay. But the only way you can really use traffic rates in the range of terabits or higher using fiber optics is that you have to do some effort to keep the signal in the optical domain all the time. Because as long as the signal is optical, it can go for a longer distance, the bandwidth is huge, and the traffic rate is very high. Okay? But at some point you have some limitation, you have to connect it to any electrical device. Once you connect it to electrical device, you have to convert optical to electrical, and that's when you have to lose. There's no way around it. Okay? So this is the limitation. So wireless, as we have discussed many times, wireless is very susceptible, is very prone to noise, is very prone to interference from the outside environment, and can be disrupted easily because, well, when you send over wireless, you send an analog electromagnetic signal in the air, okay? And depending on the type of antenna that you use, most of the antennas are isotropic, or what we call non-directional. So you dissipate the energy in multiple directions, in all the 360 degrees, which means that your power is dissipating in the whole environment. If you try to concentrate it, you will lose, because, well, what if your receiver is not in that direction? So if your receiver is in that direction, tough luck, the signal will not go there. So you are restricted with the fact that you would want to use isotropic antenna. But when you use isotropic antenna, you lose, because the energy will be divided across all directions, right? So this is the challenge here. And isotropic means that the antenna dissipates the energy in all directions. Whereas if you notice, like for base stations, have you seen like base station towers? They usually use small antennas, and each one is directional. Directional means that it focuses the energy in a specific direction. If you are in this direction, so it requires some line of sight. If you are in this direction, then you will receive a very good signal. But if you are deviated away, you will not receive anything. So directional antenna is good in the sense that it focuses the power in a specific direction, and it limits the interference, right? So the interference, the amount of interference will only be in this area, which is less compared to if you send the energy in all directions, then you get more interference. But the problem is that, directional antenna requires a line of sight to be able to communicate. So that's why base stations, they use multiple of these in different directions. But then you didn't do anything, because you have, again, to divide the power across the different directions. So otherwise, you have to increase the power. You increase the amount of power on each direction, then you get a better signal. The problem with wireless is that interference, well, the signal gets, as we said before, gets what we call modulated. Modulated means that the signal is not in the baseband. The signal has to be shifted in the frequency domain. Similar to in radios, when we tune to a specific channel, what happens is that we listen to the channel that the radio station sent over this frequency. So what happens is that each radio station or each wireless transmitter needs to shift the signal in the frequency domain to push it away from the baseband, from the low frequency, to push it in the frequency domain to a specific frequency range. This frequency range, we try to limit the interference in this range, okay? And there are certain regulations, certain regulations that says, okay, Bluetooth has to be in this range, Wi-Fi has to be in this range, and so on and so forth. The problem is that the international regulation for wireless allows only certain, very narrow frequency ranges to be unlicensed. Unlicensed means that if you manufacture any device in this range, you don't have to pay extra fees. You don't have to pay any license to use that spectrum. So people tend to manufacture all the devices in this range. So that actually creates some kind of interference. So that's why this statement says that despite the fact that we have very wide frequency range, and our limitation is whether or not we can manufacture devices to deal with these frequency ranges. But because of the regulations, people tend to focus on specific unlicensed frequency ranges, which again creates crowded wireless signals in very short frequency ranges, so the interference tends to be much higher. So that's why sometimes if you can talk over the phone and someone starts the microwave and then that disrupts your phone call. Unfortunately, it sometimes happens because of the fact that some devices, they use the same frequency, like 2.4 gigahertz. This is the most common unlicensed band on 2.4 gigahertz. You don't have to pay any license, or you don't have to deal with any regulations when you use that frequency range. So that encourages many people to use that range for their devices. In addition to the fact that it's susceptible or prone to interference, and it can be disrupted by many other devices, security becomes an issue. Why? Because we're not, again, sending a signal across a wire. So if you're tapping to the wire, then you can listen to the signal. Well, we're sending the signal over the air. Anyone can actually listen to the signal. So we cannot control who will listen to the signal, because the signal is broadcast everywhere. So we cannot control who will receive the signal. So the possibility of having someone to tap into what you are trying to send is higher in that case. It's not like when you send a signal across one wire. So it's in this wire. In order for someone to listen, someone has to cut the wire and get in between in order to. But here you cannot do anything about it. So that's why security is a very, very, very big issue for the case of wireless in particular. Many of you have discussed this in your reports already. So this is an intuitive point. So there are so many types of wireless. This is not by any chance an exhaustive list. You have many standards in wireless. Most of them are designed or coordinated by IEEE. Okay, so IEEE designs or coordinates the standards in the network access layer, or it includes the data link layer and the physical layer. Okay, and as we said, when we say the data link layer, we actually implicitly mean the MAC layer, which is medium dependent. The logical link control is medium independent. So this gets standardized separately. So IEEE, when they have standards in wireless, they usually refer to MAC sublayer and the physical layer, because the logical link control sublayer is medium independent. So they have one standard that works on everything, which is 802.2. Remember, we talked about that. So 802.2 covers the standards for logical link control regardless of the medium. So we do it once and then we leave it fixed for all types of medium. But MAC has to change from one type medium to another, and of course physical layer has to change fundamentally. So again, 802.11 refers to MAC layer and physical layer. So 802.11, of course, is the most famous, and it refers to the wireless LAN standards. And as we said before, this uses what we call carrier sense multiple access. For carrier sense multiple access, we discussed the analogy of a roundabout. So when you get to the roundabout, you listen. If someone is not going into the roundabout, if someone is not using the medium, then and only then you can access the medium at any point in time. That does not eliminate collision. Collision may still happen. If collision happens, then in wireless we cannot detect it, unfortunately. So we can use what we call collision avoidance. So we try to avoid collision, but we cannot eliminate it at all. So in Ethernet, which is what we will talk about in chapter 9 in details. In Ethernet, luckily we can detect collision, and we'll talk about how and why, because we have wire. And in the wire, we can detect if two people are actually sending on the wire. In the air, we cannot detect that. So in the wire, we use carrier sense multiple access, which collision detection, okay? And in the case of wireless, we use collision avoidance. This is the main difference. For the case of short range, for personal area network, if I want to have my own personal wireless network, for example, I have my watch and my phone, and maybe I have a heart rate measurement device or something like this, and I want to have my own personal area network. In that case, the range requirement is very small. So we can use that range to reduce the energy consumption, because all the wireless devices in that case are battery operated. So it's in my benefit to try to lower the energy consumption. So we can use the concept of short range to lower the energy consumption. How? Well, if we know that when we transmit the signal with higher power, it goes through longer distance. So since we need only short distance, we might as well reduce the transmission power. So this way we can save a lot on the battery. So we can leave our devices to live longer in that case. In some cases, this is very essential. In the United States, even before I come to Qatar, there were some commercial devices that are used for implantable. Implantable means that they do the surgery and they open the heart of a person and they put it inside. So in that case, this device has to live for years, potentially years. I'm not going to do a surgery every day for the person to get it out and recharge it and then put it back in. So we need these devices, in some cases, to live for years. So we need to have very, very, very energy efficient communication in that case. So we can. So 802.15 is the answer to this. So if we need very long range, even longer than Wi-Fi, in certain cases we need people to drive and like what we do nowadays, and we need to be always connected through wireless. I need to be able to see my email on my cell phone while I'm driving. So I need to roam, or I need to move from one base station to another seamlessly. I don't have to have any disruption in my service. So this means that we need one base station to cover a longer distance. So in that case, we have two types of standards. We have WiMAX and we have GSM. GSM is the one that evolved into what we call nowadays LTE, اللي هي 4G. So GSM is the 2G and 2.5G. Okay, so nowadays we have 4G, which is what we call LTE advanced. So WiMAX has almost faded away and given away the market to LTE pretty much. So there was a big struggle and competition between WiMAX and GSM and LTE, 3G and 4G. So WiMAX is also 4G, which means that it fulfills the requirement of 4G in terms of higher traffic and range and all of this. However, LTE, because it's based on GSM was the predominant standards since many decades back. So before people deviate to WiMAX, they have evolved GSM towards LTE and created, all the features and all the requirements that people would love to have. So in which case, they made no case for people to switch to WiMAX, and people have stuck on using LTE and 4G with the higher rates and long range and all these things. Yeah, so these are the standards in the case of wireless, and that depends again on the range that we want, and the amount of traffic that we want. If we can classify one of them into subcategories, the wireless LANs, of course, they tend to have different variations, and that depends on the fact that we can change the frequency range in such a way that allows us to limit the interference. So, for example, 802.11a works in the 5 gigahertz range. In 5 gigahertz range, this is licensed range. So you find it usually less crowded in terms of many devices that. But the problem here is that it's a trade-off, because by increasing the frequency, you always lose on the range. So the higher the frequency is, the shorter the signal can travel. So for example, from 2.4 gigahertz to 5 gigahertz, the distance will drop to almost half. We actually tried that in my research group. We tried that experimentally, and we can see that for 5 gigahertz, you lose 50% of the range right away. But it's still attractive for many people to use the 5 gigahertz range because of the fact that the device will be smaller, the antenna will be smaller, and the interference will be less. So there are some differences, some trade-offs between the two. 802.11a uses a speed of 54 megabits per second. Again, this is the theoretical bitrate. So this is the physical layer bandwidth, not the throughput. The throughput here, if you get maybe 15 or 20 or 25 megabits per second, this is great. Okay. 802.11b, this is not chronologically sorted, by the way. So 802.11b was actually designed before A. It's not because these they get designed and standardized in groups that work in parallel. So these groups, they take one standard, when they finish it, they release it. So actually B was released even before E. So E had the speed of 11 megabits per second. This is the lowest speed. Nowadays we have G and N. All the wireless routers that we have in our homes, they use G and N. The cheapest one now, they use G. We don't have B anymore. B is very, very low in terms of theoretical bandwidth. So G is comparable to A in terms of the bandwidth, theoretical bandwidth. However, G uses a unlicensed band. So G uses 2.4, which means the possibility of interference is higher in this range. However, the range for this is longer. Is longer compared to 802.11a. It's almost double the range. So if 802.11a is about 30 or 60 meters, this one is 120. Okay, 802.11n was actually designed in a later stage. Okay, and it uses both 2.4 and 5 gigs. So when you start the wireless router, it selects which spectrum to use, depending on measuring the interference in the area. So it can actually less crowded or more crowded. So it can work on either. This actually makes more sophistication in the manufacturing of the device itself. It makes the router, of course, more sophisticated in terms of design. And the typical rates for this is similar to almost Ethernet. 100 to 200 megabits per second, which is huge compared to wireless, of course. Ethernet nowadays, we have 1 gigabit per second, we have 10 gigabits per second Ethernet على wire. Over wire, it's easy. But to get these rates over wireless, this is a great achievement. Okay? And the range is up to 70 meters, which is still reasonable. Of course, it's not comparable to the range of the base stations. Base stations, you have few base stations to cover the whole country. So the range is typically around maybe 500 meters or 300 meters or something. But 70 meters is still reasonable to cover a good area.
So how is G comparable to A? They are in the same speed? Because it's different, like in the range, they're different.
Yeah, the physical layer has to be designed in such a way that gives you this speed. This speed, by the way, gets controlled by so many things in the physical layer that we didn't even discuss in the class. So there is like modulation scheme, encoding schemes that are very, very complicated in the physical layer to be able to reach to these limits. But the main difference in the 2.4 range, why the G selected the 2.4 range, is because this is unlicensed, and in this range of frequency, the signal tends to travel a longer distance. So I gain on the range, okay, and I'm still using unlicensed band, which makes my device cheaper a little bit. Okay, so these are the main differences. Okay, so this is the end of this chapter.